Now we're going to talk about chemical reactions of alkenes. So what can we do to them to change their structure? So for chemical properties, we're primarily going to be looking at what we call addition reactions. These reactions are going to be where you add atoms or group of atoms to what was a carbon-carbon multiple bond. So it could be double or triple. We'll talk a little bit later how things change slightly with the triple bonds. So first we'll focus just on the double bonds. We can still have combustion, so we can still burn alkenes. We talked about this in detail with alkanes, so we're not going to go into detail this chapter. It's really the same thing. Polymerization is where you start linking several molecules together in a long chain to make a polymer. This is one just kind of an FYI. We're not going to go into much detail about that one either. The primary reaction we're going to talk about are these addition reactions. So we can break addition reactions into two categories. We can add a symmetrical molecule or an unsymmetrical or asymmetrical molecule. So examples of symmetrical molecules are things like H2. So what we mean by symmetrical are both atoms in this small molecule are the same. We also have Br or Cl2. So both halves are equivalent. So that's what a symmetrical molecule would be. For asymmetrical, we can have something like HBr, HCl. So one half is hydrogen, one half is the halogen. Or we can have water, which we can split into hydrogen on one half and then OH for the other half. So first, let's think about the symmetrical addition reactions. So what's going to happen is you've got your carbon-carbon double bond in either case. And what you're going to do is you're going to go from that carbon-carbon double bond to just a carbon-carbon single bond. So previously there were 4 things attached. Still have those same 4 things attached. That part doesn't change. But by getting rid of the double bond, now I have room to add one atom to each of those carbons that used to have the double bonds. So for the symmetrical addition, you're just going to put one atom of each half on each carbon. So if I'm going to add the H2, I add one hydrogen to each carbon. If I'm going to do the halogen, so if it was bromine, for example, I would add one bromine atom to each carbon. So adding the hydrogen, that reaction is called a hydrogenation. And what you do is you go from the alkene to the alkane, which is carbon-carbon single bonds. You do have to have a catalyst, and the catalyst is typically nickel or platinum. Palladium is also an option. For adding the halogen, that's called halogenation. So kind of look at the word. Halogen is in halogenation. Hydrogen is in hydrogenation. And what we end up with the halogenation is a dihaloalkane. So again, the double bond is gone. It's an alkane. We've had 2 halogens, so it's called a dihalogen. So the symmetrical is pretty easy. You essentially erase the double bond, add in the 2 new atoms, and you have your product. For the asymmetrical options, we're going to have a couple of possibilities for the answer, one of which is going to be right, one of which is going to be wrong. So we need to decide which is which. So again, we're going to start with a double bond. That double bond has the 4 things attached to it. I'm going to go into a little more specific example here so we can just see how there is a difference in possibilities. So I'm going to make this double bond have 3 carbons attached and 1 hydrogen. So again, I'm going to get rid of the double bond and make it a single bond. What was attached is still attached. Again, I have room for 2 new bonds. And if I think about the hydrohalogenation, I've got hydro is the hydrogen, halogen is the halogen. So if I think about HBr, I can add hydrogen to one of the carbons and bromine to the other. So one option would be to put the hydrogen on this left carbon, bromine on the right. I could do the kind of opposite of that. Oops. And add the bromine on the left and the hydrogen on the right. So notice the difference. In this example, the hydrogen was added to the carbon that had 2 carbons attached to it, and the bromine was added to the carbon that had 1 carbon and 1 hydrogen. If I look at the second example, bromine is now added to the carbon with 2 carbons, and the hydrogen is added to the one with a hydrogen and a carbon. So these are 2 different structures. They're actually isomers of each other. One of them is the product you will get, one of them is not. So the way you decide is we have what's called Markovnikov's rule, and it's written up here in the original slide. So what it says is you need to put the halogen on the carbon atom of the double bond that is the most substituted, meaning the one that has the most carbons already attached. Another way you can say it is the hydrogen needs to go on to the carbon of the double bond that already has the most hydrogens. So in this example, this carbon of the double bond had 1 hydrogen, the other carbon had none. So the hydrogen goes to the carbon with more hydrogens, the halogen goes to the carbon that's more substituted. So this is the correct structure for this specific example. If I look at the other one, the bromine was put on the carbon that was containing a hydrogen versus the carbon that has no hydrogen that's more substituted getting the new hydrogen. Okay, so that was a lot of words. We'll look at some more examples to try to clarify that a little bit. So here's that Markovnikov's rule written out. So this is only going to apply when you have that unsymmetrical alkene. Sorry, not the unsymmetrical alkene. You're going to have the unsymmetrical molecule that you're adding. So either the H halogen or the water. When you put those groups on your original structure, the hydrogen atom from your small molecule that you're adding becomes attached to the unsaturated carbon, which is the one that already has the most hydrogen atoms. So the carbon of the double bond that already has the most hydrogen atoms. So let's look at some specific examples. So here are several. So we need to look at the reaction and decide what's happening first. So this first one, I have my alkene, the double bond, and I'm adding HCl. So this is a hydrohalogenation. It's asymmetrical. I'm going to add hydrogen to one carbon and Cl to the other. So what I suggest you do is redraw the structure without the double bonds, remembering which 2 carbons had the double bond. Now, if I look at these, I'm actually going to go back and look at the original structure first. If I look at this left carbon of the double bond, I know that it has to have 1 hydrogen. That's not shown because it's line angle. And I know that because that carbon only had 3 lines drawn to it, or 3 bonds to carbon. So to get to 4 bonds that it has to have, I know there's a hydrogen there. So I'm going to bring that hydrogen along in the product just so I can see it. If I look at the other carbon of the double bond, it has 4 lines drawn to it, meaning 4 bonds to carbon. It's already full. There are no hydrogens. So now what I have drawn for my product is exactly what I had to start with the double bond removed. So now if I look at the left carbon of the double bond, I see that it has 1 carbon, 2 carbons, and a hydrogen. If I look at the right carbon of the double bond, I see that it has 3 carbons attached. So when I decide which carbon is going to get the hydrogen, which one's going to get the chlorine, Markovnikov's rule says the hydrogen is going to attach to the carbon that already has the most hydrogens. So in this case, it's going to be the left carbon of the double bond. So I'm going to put the new hydrogen there, and then the chlorine is going to be added to the other carbon of what was the double bond. So there's my structure. If I clean this up, here's what the product would look like. We don't technically need to show the hydrogens in a line angle structure. They were just there for us to remember that they were there and decide where to put the new hydrogen. If I look at the second example, now I am adding water. Oops. This H2SO4 that's written over the arrow is a catalyst. So much like with hydrogenation, where it was the nickel, palladium, or platinum, with hydration, we need to add the sulfuric acid catalyst as well. It is not part of the product. You will not see it in the product, but it does need to be there for the reaction to occur. So if I look at my original structure, the 2 carbons of the double bond, the one on the left has 2 lines drawn to it, so 2 bonds to carbon, which means it also has 2 hydrogens. If I look at the carbon on the right, it has 3 bonds to it, so there's 1 hydrogen. So I'm going to redraw this, include those hydrogens, but get rid of the double bond, remembering that these are the 2 carbons that I'm working with. For hydration, 1/2 is going to get hydrogen, the other half is going to get OH, and the carbon bonds to the oxygen. So again, thinking about Markovnikov's rule, if I look at the left-hand carbon, it has 2 hydrogens attached. If I look at the right-hand carbon, it only has 1 hydrogen attached. So the one with 2 hydrogens is going to get the new hydrogen attached to it. The one that has 1 hydrogen will get the OH group attached to it. So if I redraw my structure, this would be the final answer. So again, I added hydrogens to the carbon on the end, and I added the OH to the inner carbon of what was the double bond. The next example, I see that I'm adding H2, and I've got a nickel catalyst. This is the hydrogenation. This is a symmetrical addition, so I don't need to think about Markovnikov's rule. I don't need to worry about what is attached to the original double bond. What I'm actually adding are hydrogens, which with line angle we don't draw. So with hydrogenation and line angle, it's really as simple as just erasing the double bond. That is your structure. You're going from the alkene to the alkane. If we think about what was there, just so we can see it, there was 1 hydrogen on each of those carbons. Now I'm going to add another hydrogen to each. So just showing those hydrogens on these carbons for detail. That's what it looks like. Again, simplifying the structure to an accurate line angle would be this. So if you see hydrogenation, adding H2, you really are just erasing the double bond. Here are a couple more examples. So go ahead and pause the video and see if you can draw the products of these 2 reactions. All right, here are the structures for the products for these 2. The first reaction is symmetrical. So both carbons of what was the double bond are each going to get an atom of bromine. The second one, the hydrohalogenation, it's asymmetrical. So I do need to think about Markovnikov's rule. The carbon on the left of the double bond did have 1 hydrogen. The one on the right had none. So I'm going to add the new hydrogen to the one on the left and the bromine to the one on the right.